Good afternoon, everyone. This is week 1, lecture 4, partial derivatives and total differential. In the previous lectures, we tried to derive the the derivatives of certain functions, and we also try to deal with different types of functions, algebraic functions, logarithmic functions, exponential functions, and transcendental functions. So we have done all those ones, and today we are going to take a look at different functions. In economics, we have functions with more than one independent variable. That is to say, the dependent variable depends on a multiple variables. Depends on a lot of variables, more than one or two variables. For example, the utility, if a consumer is faced with two commodities, say X and Y, and he has to choose between those two goods, then the utility function there, U, is going to be a function of those two goods, say X and Y. So that's a function with more than one independent variable. So the question therefore is, how do we obtain the derivatives of these functions? We are not only faced with a function with one independent variable, say y equals to 2x plus 4, or y equals to x squared plus 3x plus 4. So we do have certain equations or certain models that have more than one independent variable. So the question therefore is, how do we go about to obtain the derivatives of those functions? It is quite easy. So, but what we need to do here, we need to build from what we have studied before in functions involving one independent variable. So we are going to build from there. We use the general rule to obtain the partial derivatives, the partial and total derivatives. The essence of this topic is that most of the models that we're going to be using are models with more than one independent variable. So we are going to have the utility function as a function of two variables. We're going to have the production function as a function of labor, capital, and maybe land. So we have like the outputs depending on labor, the land, as well as capital. So in such a situation, so how do we go about obtaining the total derivatives or the partial derivatives of those functions? So this is what we are going to study in this particular lecture. This is what we are going to take a look at in this particular lecture. So we want to find maybe the equilibrium of the consumer. That is to say, the marginal rate of substitution equal to the relative prices of the two goods. MRS equals PX over PY, or MUX over MUY equals PX over PY. So how do we go about obtaining all these ones? We can only obtain this equilibrium point, the equilibrium of the consumer, the producer, if we know how to obtain partial as well as total derivatives. So this is the essence of this particular topic. So if we know how to obtain the partial derivatives as well as total derivatives, then it will be easier for us to study the consumer behavior as well as the producer behavior. So let's go ahead and get started. Now, as I said earlier, differentiation can be extended to a function of two or more independent variables. It is not only restricted to a function of one independent variable. It can be extended to a function involving more than one independent variable. And so that is what we are going to study in this particular lecture. So most times in economics, models are expressed as multivariate functions, as in the case of the multivariate demand function. So we have the multivariate demand function, we have the multivariate production function, and we also have the multivariate utility function. So most of these models express this function as a function of what? More than one independent variable. So let's take a look at one typical example here. We have a demand function, the demand for a commodity, expressed as QD equals function of PD, PX, Y, where PD is the price of the commodity. We call that one the own price of the good. And then PX is the price of a related product. It could be a substitute, a complement, either I say complementary goods or substitute goods. So the price of other goods or related goods. And then the income of the consumer. Because what we normally buy depends on what we have. So the demand for a good depends on our income as well. So in this particular case, what we do here in partial differentiation or partial derivatives, in order for you to obtain the partial derivatives, what you need to do is to differentiate the function with respect to the independent variable that you are interested in, and then holding all the other variables constant. Now, let's take, for example, you have a function with three independent variables, and you want to obtain the partial derivative of one of them. Let's say PD, right? So what you need to do is you are going to only differentiate the quantity demanded with respect to PD. And then you hold all the other variables, that is PX and Y, constant. You hold them constant. That does not mean that they are constant. You are just holding them fixed. You understand? So when you hold them fixed, it doesn't mean that those variables will collapse from the equation. It is not like having a constant term which is like 10 or 20. So it is different, right? So many a time you will see when you differentiate a function with more than two variables, you will have all the variables as the derivatives. So we're going to see that one shortly. Now let's look at this first example there. So for all partial derivatives, the notation is given as 1. Now, if you can see, you see the curly D here, right? Now, this tells us that we are differentiating the function with respect to one variable, holding all the other variables fixed. That's why we have the curly D here. It is different from that D when you are just differentiating one variable with respect to the other. Function with only one independent variable. For example, y equals to x squared plus 2x, something like that, right? So it is different here. Here, we are using the curly D here, this curly D, to symbolize the partial derivative. The partial derivative. So that is why we are using the curly D. It is not the real D that we use when you differentiate. So we use the curly D here. That it means that we are differentiating the entire function with respect to only one independent variable, holding all the other variables constant. So that is the reason why we have this notation. So I want you to pay attention to this very, very carefully. Pay attention to this very well. It is very, very important. It is very important. I want you to pay attention. Now, we see the demand function was given as a QD. Previously, we say the demand function was given as what? QD, right? QD equals a function of the price, which is PD, and then the price of related products, PX, right? And then we have income, right? Income, right? That's it. So this is the function. So what we are saying here is we are differentiating this whole QD with respect to PD, holding the other two variables PX and Y constant. Now look at my Y. Look at the way I'm writing my Y. Oh boy. So that is the function, right? So the partial derivative of this demand function with respect to the price PD is given as what? F PD. You see the small f PD, right? F PD. And then this equals to what? The F PD QXY, PXY, and then the PD. So that is the derivative. That is the symbol for the derivative, the partial derivative, with respect to PD. And then the next one is we want the partial derivative of the quantity demanded with respect to the price of the related good, which is PX, right? Again, we do the same thing, is FPX. That is the symbol. And then the derivative is what? The FPD PXY PX. Now, remember, when we are differentiating here with respect to PX, we are holding what constant? The price of the commodity and then income constant. You understand? When we are differentiating quantity demanded with respect to the price, PD, we are holding the price of related good and income constant. You understand? Now, let's look at the third equation. The QD, the QD, the Y. Oh, sorry, this one should be Y. I think this was a typo. So please omit this one. It should be Y. Oh my God, this one should be Y. So however you are so careful, you make some mistakes. This one should be Y. I just copy this one and paste that. So I did not change this one. So this one should be Y, right? So it is dy. It is not dpd. It is dy, right? So this is the qd dy, which is equals to f y equals the f pd dxy dy. Now, many a times you're gonna be seeing me putting f prime, f prime. F prime is also the derivative. Okay, so don't try to confuse yourself. You put f prime, you put this small f, and then subscript y is also the derivative. Okay, so these are the differential, the partial derivatives. Now let's move on. So it is a very easy topic to understand if only you pay attention. It is not difficult. I can assure you, I've taught this many times. It is so easy, and maybe it is easy for me. It might not be easy for you, but I believe with practice, if you continue to practice this one, you will own them. You are going to own this one, I'm telling you. If you keep on practicing, you are going to own it. So now, to get a good grip of partial differentiation, let us now try to look at certain examples. We want to maybe look at a Cobb-Douglas utility function, and wherein an individual spends his or her income on maybe two goods. Let's say at the end of the month, when you get your, or let's say at the end of the week, when you get your weekly pay, so you want to only spend your money maybe on two goods, right? You want to spend them on two goods, like let's say X and Y. So then the utility, the model there, the utility for that hypothetical consumer, U of XY, is giving us what? X to the alpha, Y to the beta. So this is the Cobb-Douglas utility function. Now, this was given, this one, Cobb-Douglas, came about by two famous economists, Cobb and then Douglas. So they were able to model this type of utility function. So this Cobb-Douglas utility function, U of xy, is equals to x to the alpha and then y to the beta, where x is the consumption of good X, the amount of X that is consumed, and then y is the amount of Y that is consumed. Now, alpha and beta are parameter estimates. They are referred to as what? The share of the expenditure on each good. They represent the share of expenditure on each good, the share of the consumer's expenditure on each good. Now, when you get your income, you're not going to spend all your money on, let's say, X. You're going to spend part of your income on X, and then you spend the other one on Y. So the share of that income on these goods, on the expenditure on these goods, is given as what? It's your alpha and your beta. So these are all parameter estimates. So we're going to look at this one later on when we deal with the consumer theory. The partial derivatives of the student utility function can be expressed as what? U of x, which is equals to the u xy dx, and this is equals to what? Now, it's equals to alpha x to the alpha minus 1, y to the beta. Now, I know for some of you guys, this will actually look strange. You don't even know how this one came about. It is not strange. Now, just follow me here. Look at me here, what I'm doing. So I have x and then y here, right? So what did I say before? I said when you are differentiating the function with respect to one independent variable, if you have more than one independent variable, you have to hold the other variables constant, right? So now, and this u of xy, we know it was given as x to the what? Alpha, and then y to the beta, right? Y to the beta. There you go. So you have that one, right? So we want to find u of x, which is what? The derivative of the utility function with respect to x, right? And that is given as what? The u, the what? The x, right? The x. And that gives us what here? So what we are doing here is we are going to differentiate this entire utility function with respect to x. Now you take the power or the exponent of x. You are differentiating with respect to x, right? And you are only doing that for x, not for y. You understand? You are holding y constant. So the exponent of x here is alpha. So you remember the general rule of differentiation, right? Y equals x to the power n. The y dx is what? N x to the power n minus 1. That is the same thing we're going to do here. It is the same thing. This is not rocket science. I'm telling you, it is not rocket science. You will be able to do this one at the end of this course. So, alpha here is the exponent. So we are going to multiply this whole term, x to the alpha, y to the beta, by alpha. That is the first thing we're going to do. And then we have our x. Now, do we have to leave alpha as it is? No, we have to subtract 1 from that. Minus 1. That is the rule. We are done with the differentiation there. But do we just have to write this one? No, we have to bring y to the beta down. Even though it is L constant, we need to have it in the derivative. So that is the answer. That is the result. Have you seen? So y to the beta, right? So it's alpha, x to the alpha minus 1, and then y to the beta. Even though y is L constant, we need to bring it down as we solve. So now the derivative of the utility function with respect to x is given as alpha x to the alpha minus 1 y to the beta. That is all. That is your marginal utility. That is your marginal utility, right? Now we want to do the same thing for y. What is the marginal utility of good y? Or what is the partial derivative of the utility function with respect to y? Similarly, what we do here, in fact, what I want you to do first is to make life easy for yourself. Make sure you bring the x to the alpha first, because that one is L constant, right? Bring it down. That is the derivative, right? And now, let us differentiate this y to the beta. Now, you know y has an exponent of beta, right? But the general rule says if you have y to the beta, you want to find the u dy, you have to multiply that variable by what? By the exponent beta, right? So that is why you're going to have the beta here. X to the alpha, and then y. Do we just have to write beta? No, we don't. We have to say beta minus 1, because that is the rule. You always subtract 1 from the exponents, right? So this is the derivative, the partial derivative, and that is the marginal utility. So I hope you get this one. So as I told you earlier, this is not rocket science. you will be able to do this one as you keep on practicing. It will be like drinking a cup of tea or drinking water. So it is so easy, straightforward. You don't need to go to Cambridge to know this one. So I believe this will be so easy for you, and you'll be able to articulate this very well in any exam. If I ask you to find the marginal utility, I give you a Douglas utility function, you should be able to do this one. It is easy, straightforward. So let's move on. Now, let's try to solve some problems here. Suppose a consumer spends a weekly income on two goods, food and clothing. If the utility of this consumer is given as U of FC equals F to the 0.4, C to the 0.6. Obtain the partial derivative with respect to F and the partial derivative with respect to C. Now here, we have the function is equals to what? U of FC equals to F of F 0.4 and then C 0.6, right? So what we need to do here is we are going to obtain the partial derivative with respect to F, and then we hold C constant, right? Of course, you know what to do here. Now we say our utility function was what? F C, right? All right, FC equals F to the 0.4, right? And then C to the 0.6, right? Voila. Now we want to find the partial derivative of this utility function with respect to F. Now, how do we get this one? It is simple. So I want to differentiate this function with respect to F, right? I am only going to differentiate this utility function with respect to F, and then I hold C constant. Now, since I'm holding C constant, let me first of all write the C down. That's the first thing I have to do. The first thing I have to do, write that one down, C to the 0.6. I'm not going to do anything with that, right? Now, what I'm going to change here is this F to the 0.4. Now, the F to the 0.4 now becomes what? We have to multiply the F to the 0.4 by 0.4, the exponent, the general rule, right? So we say 0.4 F, and then raised to the what? 0.4 minus 1, right? Always, that is the law, that is a rule. If you follow this rule, you are not going to miss this problem. You are always going to get it correct. So don't say because now if we have used this rule, and then you are going to say, oh, okay, no, let me just forget about Alim's method. Let me just say 0.4 plus 1. You are not going to get the answer correct, because that is not the rule. That is not the norm. Okay, let's go according to the norm here. So, and if we solve this one, we're going to have 0.4 here, F. Now, 0.4 minus 1, of course, you know is what? It's minus 0.6, right? Yes. 0.4 is less than 1, and you are taking a number that is greater than a number greater, you are taking 1 from a lower number, right? So in math, the greater number carries the sign. So if you say 0.4 minus 6, just say 1 minus 0.4. 0.4 minus 1, just say 1 minus 0.4, which is what? 0.6, right? But because 1 is bigger than 0.4, so and it has a negative sign, you have to put a negative sign in front. And then you have C to the 0.6. There you go. That's your answer. That is your answer. It is so easy. It is so easy. It's like drinking a cup of tea. You know, you don't need to be labeled with this one. These are simple and straightforward. Okay. Now let's look at the next one. If you differentiate with respect to C, clothing, you are going to hold what? Constant F. This time you are going to hold F. So since I'm holding F constant, right, and I have F to the 0.4, let me first of all write it down. F to the 0.4. Simple. You're done with that. And now you differentiate with respect to C, right? Now what do? You take the 0.6 and then you multiply by this whole function now, 0.6, F to the 0.4, C, and then 0.6 minus 1 is minus 0.4, right? So that's your answer. So that's how you derive the partial derivatives. It is so easy, so straightforward, and I believe these ones will be like drinking a cup of tea in the morning. Okay. Now question for you. I want you, when you have time, please, when you have time, make sure you are able to answer these questions. Make sure you are able to answer these questions. Go over them, answer these ones. These are meant for practice. Make sure you are able to practice them, find the partial derivatives. Now, with respect to PD, PX, and Y, do the same thing here. Now, if you look at these two equations, they are the same. The only difference is that these ones are the second one is using numbers for the parameters, and then the other one are giving us actual parameters, right? So now I want you to go home and then make sure you solve these ones. Get the partial derivatives, get them, derive them, and study them. Make sure you know how to obtain them, okay? Because in all your tests, in all your exams, you are going to derive them. You are going to obtain the partial derivative. You are definitely going to do that. Okay, so I want everybody to ace the exams, ace the test. You can only ace the exams and the test if you work very hard. I know for some people are saying that the work is too much. Yes, it is too much, but you are going to gain something. So this is not a high school. This is the university, and we have to set certain standards. We need to maintain some standards. Okay, we need to maintain standards. So it is not just okay for the whole here, the whole semester. I'll give you like one exam, maybe one midterm, and then one final. No, I need to, make a thorough assessment of you guys. Make sure that you don't only pass the exams, you don't only pass the course, but you are able to know something. You're able to have something in your head. Okay? So it is not just like, oh, I've passed this exam. You're done with it. It has to be with you. You have to go with it. Okay? Now let's move on to total derivatives. As in partial derivatives, we have we know what to do here. We know how to obtain the partial derivatives now. You differentiate the function with respect to one variable, and then you hold all the other variables constant. Now, we do the same thing here. We do the same thing here. So, but what we do here is we are going to find the total derivatives of a particular function, let's say the dependent variable, with respect to the independent variable, right? We find dz, we find dz, and then we have f of x dx plus fy dy, fx dx plus fy dy, and that gives us what? Dz, right? Now remember, fx is the partial derivative, and then fy is the partial derivative with respect to y. That's right. Now, what do you observe here? There is a different notation here. Remember, the partial derivatives, we are using curly d's here, right? But here, we are going to use the actual d as the derivatives for a function with one independent variable. So we have the z here, which is equals to fx dx plus fy dy, right? So if you have a function with more than one independent variable, you first of all find the partial derivatives with respect to each of those variables, and then substitute them into the total derivative. So that's how you get the total differential. Now, the essence of total derivatives here is very simple. The essence here is we want to know what will happen when the farm is moving along the isoquant, or when the consumer is moving along the indifference score. So if you move along the indifference score, the utility, the consumer gets the same amount of utility. Along the same indifference score, the consumer derives the same amount of utility, and so the total utility there should be 0. In other words, the total utility is constant. Because the consumer is deriving the same utility, because the consumer, now what I'm saying here is that if we have, let's say, an indifference score, we have an indifference score. This is the indifference score. It is convex to the origin, right? So we call this one IC1, indifference score 1, right? So we have y here on the vertical axis, and then we have x on the horizontal axis, right? So if the consumer is, let's say, we're here, right? Okay. Then we have this amount that is consumed. Let's say this is 10 units of y consumed, and this is, let's say, 5 units of x consumed, right? Now, let's say this is point A. You have point A here, and then you have another point. Now, the consumer decides to move to point B along the same indifference curve, right? Let's say the consumer decides to move along the same indifference curve, right? So let's say this is 10, and then this is what? This is 5. There you go. Now, the consumer is moving from point A to point B. So along this point, when this consumer is moving along this point, right? Along this point up to point B, he is getting the same amount of satisfaction. He is getting the same utility. You understand? So if you have a function, you have a utility function u of xy, right? And then you have the total derivatives here, the total differential du here, which is equals to u of x dx. That is u of x, the partial derivatives, u of x dx, plus u of y dy right? Equals to the total derivatives here. Total derivative, which is du. So along the indifference curve here, from point A to point B, the consumer derives the same amount of satisfaction. So as a matter of fact, by definition, the total differential here, the u, is equals to 0, because along the same indifference curve, the consumer derives the same utility. Now, if you plug this 0 into this total utility function, you're going to have what? 0 equals u of x dx plus u of y and then dy, right? So if you bring the u of x dx to the other side of the equation, you're going to have negative u of x dx, right? And then this equals to u of y dy, right? U of y dy. So what do we do now? We want to find the y dx, right? The y dx here, which is the marginal utility, right? So all we need to do is to divide both sides by what? U of y and then u of x here. You have minus u of x over u of y, and then you divide both sides by, or you multiply throughout by what? By uy over dx, right? Uy over dx here becomes dx dy, and then uy cancel. Uy over dx here, dx cancel, and then you have over y, right? Okay, so so you have dx what am I saying here is oh, okay, you multiply by 1 over uy dx, right? And then again here again by uy 1 over uy dx, right? 1 over uy dx, uy cancel the uy, you are left with dx, and then 1 over uy dx, the dx cancel dx, you are left with what? Minus uy, ux over uy. So you have minus ux over uy equals dy dx. So this dy dx represents what? The marginal rate of substitution. The marginal rate of substitution. The rate at which the consumer is willing to substitute one good for the other and stay on the same indifference curve or derive the same amount of satisfaction. Okay? So, the total derivative of this dependent variable z is obtained as z equals fx dx plus fy dy. So, the total derivatives f of x equals dz xy dx, fy equals dz xy dy. Now let us consider a utility function given as this one, u equals to uxy. Then how do we get total derivative here? As I said earlier, the total derivative here is what? Du equals u of x, which is what? Du xy dx, and then the x, and then u of y is what? Du xy dy, right? Which is uy dy, right? So u of x here, the u xy dx, which is the marginal utility of x, and then u of y is the u xy dy, which is the marginal utility of y. So if we plug that one here, we get the total derivative. Okay? So this is the total derivative of this particular function.